12.1 vector valued functions. We will talk about vectors with respect to a function introduced in algebra. Typically, a long time ago, when you talked about a function, you only talked about one function, some f of x, if you will. Here we introduce what we call a path vector or a position vector, R of t. And this path or position vector, if it's in the plane, that is x and y, it is being produced by some vertical direction that we call I. So it has a function attributed to it, f of t, and then some horizontal that we call the y, or here, j, for the y-axis. Then it has a function attributed to it, and it's g of t. If we're in the space x, y, and z, then we pick up a third function, h of t. Yes, sir. Yes, sir. Yeah. K represents the. You got it. You got it. Yep. I, J, and K represents X, Y, and Z axes. Yes, sir. So the name vector valued here, denoting the I, J, and the K, and those positions give us some type of vector notation. And then the functions would be f of t, g of t, and h of t. So you think about f, g, and h as Math 112 or Calculus 1, okay? So whatever you did to a function back in Calculus 1 for some function f, if this is a position vector r, you do that same thing to f, to g, and also to h. So all the rules and principles for Calculus 1 applies here. Obviously, hence the name Calculus 3. So you can write the vector notation. If you wanted to use I and J or K, you can use that, or you can use this notation, and this notation is said to represent the vector notation. It looks like you get this sideways V on either side, and so if you see that, you think the first position is the ith position, the second variable here expression is the jth, and if it's in the space, then you have the f of t represents I, g of t times j, h of t times k. So just another way of writing the vector value function. We say that the so-called vector value function, or the path or position vector, it roams through space in some path, and we call that path a curve C. Now, what is that curve C? That curve C is going to be what we talked about in chapter 11 with the cylinder. Remember, the cylinder was said to be a curve intersected with some kind of parallel rulings. So we said that cylinder, if I have a particle moving with respect to that cylinder, or in the path of that cylinder, we say that particle moves along the curve, that curved line. So later on we'll talk about C, whether or not it's smooth, if it has derivatives, if those derivatives are continuous on that particular path, we say that it's smooth. And later on, we start to deal with some of the classic theorems here in analysis, that is Green's theorem, Stokes, and the divergence theorem. They'll be concerned with the nature of the path. And we'll talk about all of that. So here, let's look at just some basic problems. First, we note here limits and continuity. The definition for the limit and the definition for continuity here in Calculus 3 is the same definitions for the limits and continuity in Calculus 1, but just with respect to the various functions with respect to the vectors. So here, r of t, its limit as t goes to a, is said to be tantamount to the limits of f and the limits of g as t goes to a, if that's in the plane. If it's in the space, then this limit of r of t is said to be the same thing as the limit of f of t as t goes to a with respect to I, plus the limit of g of t as t goes to a with respect to j, and then the limit of h of t as t goes to a with respect to k. So what are we saying? We're saying that the way you found limits in Calculus 1, do that same thing, but here you apply it to this f, to that g, and to that h. And you do the limits separately, right? And so what in the general scheme are they saying here? What they're saying is that if I take the limit of a vector value function, the result is also still a vector value function. That's the key. We talk about, the derivative is based on its definition is based on the limit, and so the derivative of a vectored value function is also still a vectored value function. Now, continuity, same definition in Calculus 1. A vector value function R is said to be continuous at the point. It's either continuous at a point or it's continuous on an entire interval. If it's continuous at the point given by t equal to a, there's actually three things going on, but here they just say it in one statement. That is that here the limit of RT exists. Sometimes the limit may exist and you don't know what it is. That's okay. The limit of RT exists. R of A is defined. That is that I can evaluate the function vector R at A. And then thirdly, the limit of R of T as T goes to A is precisely R of A. So we used to talk about this definition of continuity in three ways. We said first that the limit as t goes to a of R of t, that this guy is said to exist. What is it? I don't know. And then we said, secondly, that R of A is defined. And then thirdly, we put the first two statements together, and we said that the limit as t goes to A of R of t is equal to R of A. So that's what this definition is saying. It's saying three things in one. The limit exists. I may not know what it is. You remember in Calculus 2, because I'm making a statement here that the limit exists and you might not know what it is. In Calculus 2, we talked about, we didn't tell you exactly what it was called, but we were talking about it. We talked about what's called in analysis the existence of something. We could talk about theorems that are said to portray the existence of something, and then we could talk about theorems that talk about the uniqueness of something. So theories and analysis said to be classified in either the existence of a thing, that it exists. Now, what it is, you might not know. It may be difficult to find out what it actually is. And then, secondly, if I can find out that something does exist, does it stand alone? Is it by itself? So if I say that the limit exists to this point, does that limit also go somewhere else too? So then I have trouble. And so I may have bifurcation, and so if I have that, then it might not be even defined as a function if that's happening. So either something exists or even something stronger that is unique. In Calculus 2, you recall in chapter 9 when you started dealing with those series. Remember the series? And then you had the whole question of whether or not a series was convergent or divergent. Do you remember in some of those, you could not figure out its limit, but you could tell based on whether it was direct comparison, indirect comparison, whether you use, say, for example, the P series, something like that. You can tell that it was convergent. But if you think about it, go back and look at it, with some of those, you were never asked, what's this limit? Only whether or not it was convergent, divergent, or if it was conditionally convergent, or if it was absolutely convergent. But in some of those, the question was never, what's this limit? Some of them were. And you could get the limit if it was a telescoping. Remember that? If it was telescoping, I could find the limit for that. That is that the limit was actually the sum of all those terms, all the middle terms canceled out. So all you had left was that first term and that last term, which was a limit, right? Based as that got tilted to infinity. You can actually find that limit. Right? You could use the nth term test for divergence, and you could determine something like that. Or if it was geometric series, you had a formula for that limit. But for the rest of them, you didn't. So for the rest of those guys that you didn't have a formula for the limit, you were actually using, in this real big scope of mathematics, what's called an existence theorem. I know that is convergent. I know the limit exists. Now what it is, I don't know. Matter of fact, you didn't care. You know? Right? Yeah. Now, what's the power of that? And how far can you go with that? You can go a very long way with that. And in archaeology, they use that theorem, the existence theorem, to prove a lot of things based on what happened 1,000, 2,000, 3,000, 4,000 years ago, because we wasn't there, or whatever, how long you want to go back. And here's what they do. They say this. Here's an argument. The argument could be this. Did the people of Israel, were they ever actually slaves in Egypt? From an outside point of view, just using science, we argue that, whether it's yes or no. You have one claim in Scripture that say that this is true. But then can you find other artifacts that either support that or disprove that? With that same argument, you argue if Israel, if they were actually in Egypt for a time, if they were slaves there, you add to that, is it true that when Israel left from Egypt and they crossed that peninsula, that they crossed the Red Sea? You raise that issue. Is the Bible true? And what it says that when they crossed, that God dried up the ground in the Red Sea. You argue that. Did these miracles happen that followed Israel? Here is how the existence theorem comes into play. It's very simple. It's very simple. What the mathematician does is he comes along. He says, look, we don't have to prove all that. We just prove one thing. Just prove one thing. Prove one thing. If you can find that this one claim is true, that gives credence to everything else. Here's his argument. Did Moses exist? He's the one writing the stuff. Can you prove that Moses existed? If you can prove that he existed, case closed. If you can prove that he did not exist, if there is not a Moses, then everything that's said about all these events fails. That's an existence theorem. I want to tell you, and biblical studies in graduate school, it's been proven. I have archaeological books outside of Scripture that proves that there was a Moses. I'm through with that. I'm through with that. We ain't got to prove nothing else. You know? I mean, that argument, it goes alongside did Phil Talbert Sr. exist? That was my granddaddy's daddy. Yeah. Did he exist? Well, his son existed. His grandson existed. I got proof of his great grandson because I'm right here. So it must be true that Phil Talbot Sr. existed. So, and for the existence, you don't have to go into detail with this or that. You just prove that the existence of something is true. So here, that's what that first claim is saying. So I said a whole lot to say that there is a lot of power in these statements. That first statement just says that R of t exists. The limit of R of t exists as t goes to a. You may not know what it is, but for continuity, you got to know. If a function is continuous, we say that the limit of R of t as t goes to a is exactly R of a. Well, let's move on. So let's look at some problems. Find the domain of a vectored valued function. Here the domain, you recall from earlier math, if it's a polynomial and it's not rational, if it's a polynomial, then the domain would be all real numbers. If it's some function that's rational, then you know that when the denominator is equal to 0, it's not continuous. So I don't have anything happening there. And so that's the only value that you're concerned about here for this first form, 1 over t plus 1. If t is equal to -1, is discontinuous. So the domain would be all real numbers except -1. So here our domain, is it writing? Now it wants to write. Oh, it's better than mine. We say all t such that, and it's a couple of ways you can write that, but we'll just say, I'll write it two ways. Here, where t is not equal to -1, or you can say from -infinity to -1 union from -1 to positive infinity. So a couple of ways you can write that. You move to this next one. We look at its domain. The domain here is restricted by what's happening under that radical. We know that the radical, the terms under that must be positive. So we know that 4 minus t squared has to be greater than or equal to 0. Now you could break that up. If you've seen that before, and I'm assuming that you have, you know how this guy looks. If you want to play with some points, look at the interval. The interval is from -infinity to -2. So you get that here. You get t equal to 2, t equal to -2. So we're going to chop the number line up based on those values. And then we go to positive infinity. If you take a number on the interval from -infinity to -2, let's take -5, plug that in for t. So I get 4 minus 25, you get negative. Take a number between negative 2 and 2, let's say 0. 4 minus 0, I get positive. And then a value bigger than 2, obviously 4 minus t squared would be negative. So where the function r of t is positive, no concern with t squared j and negative 6t. Those values are true for all real numbers there. Only time we have restriction is if it's a fraction. I look at my denominator. If it's a radical of the of an even root, like square root, fourth root. No concern about the cube values, the cube roots, because they maintain their sign. Negative goes to negative, positive goes to positive. And then also there's restriction with, say for example, trigonometric functions. If it's 1 over 0, then we have something that's said to be an isotope, or basically undefined at that value, but it may be isototic. So here my domain would be from all values of t from negative 2 to 2. So here for all t, such that you could say this, that here, why is it doing that? Negative 2 is less than or equal to t less than or equal to 2. Or you can say closed interval from negative 2 to 2. So either way you want to say it is fine. Any questions? Let's look at the next one. Evaluate the vector value function at each given value for t. So let's take part A. We're going to find r of 1. So this is 1/2 times 1 squared I minus parentheses 1 minus 1j. So that just gives us 1/2 I. The 1 minus 1 goes out, and so that's all we have there. Part B, r of 0. So this is 1/2 times 0 squared I minus 0 minus 1 times j. Well, the ith term goes out because that's just 0 times it. And then this jth term is negative times a negative. It's just 1j. You can just write j. Yes, sir. R evaluated at 1. T is equal to 1. Yes, sir. Part C, R of s plus 1. So wherever I have t, we're going to write s plus 1. So this is 1/2 parentheses s plus 1 to be squared I minus s plus 1 minus 1 j. So we can clean that up. R of s plus 1 is equal to 1/2 s plus 1 squared times I, and then this is minus s times j. Now part D, where does that come from? Part D, have you seen that before? The whole thing for part D, that comes from where? As my Aunt Daisy used to say, "Oh, I better sit down." Yes, sir. Okay. All right. Let me see if I can help you out. Part D, better write that guy first. This is R of 2 plus delta t minus R of 2. Do you recall, I'm writing R, but maybe I can write it in a way that is familiar to you. F prime of, yes, sir, definition of the derivative. It's the numerator, right? Yes, sir. F prime of x is equal to the limit as, let's see here, this guy would use delta x. As delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Okay? It's all coming back to me now. Yes, sir. Difference quotient. And Math 112, we talked about it there, the difference quotient, where we didn't put the limit in front of it, right? And so the difference quotient in what it is graphically is the secant line. And then once you take the limit of that, you shrink that secant line to just a point, and we get the tangent, the derivative. Yes, sir. I got to go up there too and write the function again. You got it? Okay. So for this problem, we want to find this difference. This is R of 2. Well, let me write R of t because I can't see it. Oh, got it on my paper. I can write it from my paper. It's 1/2 t squared I minus t plus 1j. Is that right? 1/2 t squared I minus, oh, there's a minus there. All right, good. So we'll find this in parts. Let's just find R of 2 first. That's the easiest one. So this is 1/2 times 2 squared I minus 2 minus 1j. So this is 2I minus j. And what about R of 2 plus delta t? This is 1/2. Wherever I have t, we replace t with 2 plus delta t. This is 1/2 times parentheses 2 plus delta t to be squared I minus parentheses 2 plus delta t, then that's minus 1j, and we simplify that. Delta t, 2 plus delta t minus 1. You know, we replace, yes sir, down here. Right. Delta t. Okay. I'm saying t, I wrote x, but it's supposed to be. Okay. Thank you. Donnie, you must be kin to my wife. But anyway, that's boy, they pick out that little smaller thing. It's, oh my goodness. Well, Donnie, you're gonna make somebody a good husband. Bless you, man. No, I'm just teasing. India, don't think ill of me. So let's simplify this. So this R of 2 plus delta t, this is the 1/2 times parentheses. Just FOIL that out. So that's 4 plus 4 delta t plus delta t squared times I minus parentheses. 2 minus 1 is just 1. plus delta t j. And then I'm going to simplify that just one more, and then we'll put the two terms together. Just divide by 2 here, so this is 2 plus 2 delta t plus delta t squared over 2. That's all times I minus 1 plus delta t times j. Now we get what they want us to find, r of 2 plus delta t minus r of 2. So this is 2 plus 2 delta t plus delta t squared over 2 I minus 1 plus delta t j. And then r of 2 was, and is minus, so this is minus 2I minus that negative j is plus j. Let me write that, put that plus there better for my wife, I mean for Donnie, but she's gonna kill me. Okay, anyway, r of 2 plus delta t minus r of 2. So we're gonna get the i's together and get the j's together. So this is 2 plus 2 delta t plus delta t squared all over 2. Can't read that. And then that's minus a 2 times I minus 1 plus delta t plus 1 times j. And so we end up with 2's cancel there, so this is just 2 delta t plus delta t squared over 2 times I, and then this is just minus delta tj. Okay. Let me know when you get that so we can move on. Do you have it? You have it? Okay. Everybody else? Okay, good, good. So I'm going to do one more and then I'm going to give you a problem to do. Oh. Is there something down there? Nope. Well, I forgot about this page. I'll do this one. A couple more and then I give you one to do. So here, find r of t dot with u of t is the result of vector value function explained. What is r of t dot with u of t? What is that called? Dot product, that's right. Dot product or the inner product. Very good. So we find the inner product of r of t and u of t. So that becomes the 3t minus 1, and that's times, it's times each, their corresponding positions, the terms, so 3t minus 1 times t squared, and then plus 1 over 4 t to the third times negative 8, and then plus the kth parts, this is 4 times t to the third. So here we have 3t to the third minus t squared minus 2t to the third plus 4t to the third. And I think we can simplify that. We get 3 minus 2 is 1 plus the 4, that's 5t to the third minus t squared. And so the question is the result a vector value function? Yes or no? is the as a result of vector value function. You say yes. Why do you say yes? So so the result 5t to the third minus t squared. You have I, j, and k there. Yes, sir. Okay, this is okay. Um, this was chapter 11, 11.2, I think, in calculus 2. Do you remember that? That's right. Yeah, yeah. Bless your heart. Um, no, I can. It's real quick for me to explain it. So, yes, sir. Yes, sir. Is I'm going to underline what we're multiplying for the first parts. This guy is the ith part times the ith part over here. And then for the j's, I'm going to multiply those terms together. And then for the k's, multiply those terms together. They're separated by a plus sign. So the definition, um, let u equal to u sub 1i plus u sub 2j plus u sub 3k. And, this is the symbol for and let v equal to v sub 1i plus v sub 2j plus v sub 3k. So we call it, its correct term is the inner product of u and v. Um, simple term is the dot product because normally you see a dot in between. And what it's set to do is, it's the only way that we know how to multiply vectors. We multiply vectors by this dot product or inner product. So here, so the multiplication of vectors of u and v is called the inner product and for short, dot product denoted by u dot v. Now, a few problems ago, I showed you, well, the book showed you, and I was thinking I didn't like it, but he had this symbol to represent some vector terms. Do you remember that? Right. And that's not good, because in higher studies of mathematics, those symbols represent the inner product. So when I do a vector, I don't do that symbol. I just use parentheses. Yes, sir. Multiplying them and then just adding each term respectively together. So here, or the inner product of u and v. Now, what we get here, and I'll just write it how this is the inner product of u and v. That becomes u sub 1 times v sub 1 plus u sub 2 times v sub 2 plus u sub 3 times v sub 3. Okay. So that's the inner product or the dot product. So that's all we're doing. Now, this guy is said to be in the one space. So the result is not a vector value function. It's a scalar. For it to be a vector, you got to have I, J, and K. It's a vector. The cross product is a vector. Cross product is not the dot product. Cross product comes from matrices, you remember? So it's like a matrix, it's a determinant. You have I, J, and K up top. Then you have the first vector, second vector. You multiply that out, the result of that is a vector for the cross product. But for the dot product, the result is a scalar. It's just a number. Right? It's not a vector anymore. Yes, sir. Yes, sir. Yep. For the cross product, its result is also still another vector, a vector value function. Yes, sir. Yep. Mm-hmm.
The vector value function of the result of that cross product, will that function be perpendicular to the other function?
Yes, that's how it's defined. Yes, sir. And that's, again, going back to like 11.4, 11.5, where we talked about that in calculus too. But yes, the cross product of two vectors is said to be perpendicular to the individual vectors. Yes, sir. Yep. And I did put my videos from those sections in Blackboard, so please feel free to go back and look at some of that information. If you have questions, just let me know. We can go over it. Yeah. Okay. So good. So this guy, the result of I should say the is not a vector valued function, but a scalar. It's a number. The scalar is just a number. Okay. Any other questions? Here, sketch the plane curve represented by the vector value function and give the orientation of the curve. So what direction is the curve moving in? The curve will move in the direction of the value of t. T is set basically to represent time. So t will start from 0. T equals 0, t equal to 1, t equal to 2, t equal to 3, and so on. So typically what we do is we solve this by saying that x is 1/4 and y is t minus 1, and then trying to draw the connection to somehow eliminate t and have the function in x and y alone. But for this function, or for this vector value function, can't get that, because what happens is that the nature of this function is that it is a constant function. Let me show you. So we have the values for t that you pick, and then here we have x and we have y. You pick the values for t. We start t equal to 0, t equal to 1, t equal to 2 in that fashion. For whatever value of t, see how x always stays to be 1/4? X is fixed to be 1/4. for the value of t equals 0, y is equal to negative 1. When t is equal to 1, x is still 1/4. When t is 1, y is 0. When t is 2, x is 1/4. When t is 2, y is equal to 2 minus 1. I get 1. What kind of graph is that? Huh? Who said parabola? How do you see a parabola? I used to be able to kick real good, but it's a straight line. Let's look at it. Let's graph. Here we're going to graph with respect to x and y. Just plot points, right? So that's 1/4. Say it's there. So when x is 1/4, y is 0. I'm here. X is 1/4, y is negative 1. There. X is 1/4, y is 1. Here, let me tell you this, folks. Here's the cool thing about math. Let it do what it wants to do, and you just be the student thereof. Don't put nothing to it. You just let it do. And if you can't see it, try to draw something out to help you understand, what's going on. But let it do what it does. I'm not going to add nothing to it. I'm not going to take away. The prophets of old, they were God's prophet because they didn't add to what God said, and neither did they take away from it. You remember Balaam got messed up because he tried to add. When that old wicked king in Moab and Edom said, "Won't you curse the children of Israel?" And that king said, "I'll pay you a big sum of money." And that prophet said, "Okay, that money looks good." And he tried to go out there and he tried to conjure up some prophecy, and he couldn't even do it. He was trying to lie on the people of Israel, couldn't even do it. And you remember that was the situation when he was going to try to curse the people of Israel, and the angel stood up, and he couldn't see it because he was a false prophet, but his donkey saw it. And the donkey saw the angel with the sword, and the donkey held still, and Balaam kept whipping his ass. I just want to say that. He was whipping his ass, man. That's what the Bible said. That's the only time you can cuss, in church and get away with it. Anyway, it's bad. But he whipped his donkey, and then God allowed the donkey to talk. And the donkey said, "Why are you whooping me? I'm trying to save your life. Man. You don't see that man with that sword right there? He's aiming at your head. He's aiming at your head, man." And God sent the angel to prevent this false prophet from going down there lying on the people of God. So when the prophet finally got it, he said, "Look, man," he said, "here's your money back. I can't do it." He said, "I can't do it, man." He said, "My ass just saved me over here." Man, I can't, man. Oh, no. So look, man, I'm not going to add nothing to it. I'm not going to take away. I'm going to let it do. Man. So look, I'm going to let it work it on its own self out. It's a vertical line. Right? Oh, let me not put the arrow like that because I have to determine the direction. Sorry. So here, if I start at t equal to 0, I get the point 1/4 negative 1. I was here. Start at t equal to 1, I go in the direction of t. T 0, 1, 2. That's how I'll look at for the orientation. So look at t equal to 1, I get 1/4 comma 0. I'm going in this direction, right? That's the orientation. It's time. Yes, sir. Typically, that's what we represent t to be. Yes, sir. So I'm going to do this one. This is very similar to the next one. But again, you let it do what it's supposed to do. Let me work this one out, and then I want you to do the next one. So here we're going to sketch this. Again, x is equal to cosine theta. Y is equal to 3 sine theta. Now, why do we say x is that and y is that? Because here the functions r of t, that's how they're defined. This is always x of t I plus y of t j plus z of t k. So that's the definition of that position or path vector. Now, what's the relationship that I know between cosine and sine that I can use to eliminate theta to have a function of x and y alone? What's the relationship? Which would be several, but can you name one good one? In terms of cosine and sine. Yes, sir. Cosine squared theta plus sine squared theta is equal to 1. Let's use that. Okay? So we know cosine squared theta plus sine squared theta is equal to 1. Now we have a statement for cosine theta, but not directly for sine theta. So here we'll say cosine theta is equal to x, and what's sine theta equal to from up here? Yes, sir, y over 3. So if I put this information into this equation, then I end up with x squared plus y over 3 to be squared is equal to 1. Or x squared plus y squared over 9 is equal to 1. What kind of equation is that? It's an ellipse. It's an ellipse with a is equal to plus or minus 1 and b is equal to plus or minus 3. Yes, sir. Yes, sir. Right. You remember that this is x squared over a squared plus y squared over b squared is equal to 1 for the equation of the ellipse. So since a is plus or minus 1 and b is plus or minus 3, 1, 2, 3, 1, 2, 3, then I draw this ellipse. Now we look for the direction. To get the direction again, we write our chart. Zero, pi over 2, pi, we use those guys. So here, x, what is x? Well, cosine, well, t is theta, I'm sorry. So if cosine of theta is 0, so there I get 1. And then I come over here for y, I plug in theta to equal to 0. Well, sine of 0 is 0, so y is equal to 3 times 0, if you will. So that's just 0. If I use pi over 2, cosine of pi over 2 is 0. Here, sine of pi over 2 is 1, and that's, we get y is equal to 3 times sine theta. So if theta is pi over 2, that sine of pi over 2 is 1 times 3, we get 3. And then if we let theta equal to pi, I get negative 1, I get 0 there. So I look at, for theta equal to 0, I get x is 0, y is 1. I'm here. And then, I mean, you could pick several values you want for theta, but I pick the easy ones. I just want the direction, that's all. How do I get the direction? Basically, I just get 2 points. And starting at t or theta equal to 0 and going to the next point, I get that direction for t or theta. You're done. So here x is 0, y is 3. I'm here. You see how this guy is moving in this direction? That direction is said to be the orientation. That's how here there's a particle. That's what we're tracing. There's a particle moving along this path. Later on, we'll talk about the energy exerted by this particular particle. That energy that's exerted by it will be some integral that we call a line integral. And what the classic theorems will tell us later on in chapter 15 is that whether you look at the energy exerted along this path, along this ellipse, this energy here along the path is said to be equal to the energy that's being consumed within the surface of that ellipse. So you can measure either what's happening here, or I can measure what's happening there. They're both said to be the same. Now, that seems like a very difficult conclusion to come up with. It is a difficult conclusion.
Is that the interior of
Yes, sir. Yes, sir. That would be the interior of the ellipse. Green's theorem makes that claim. His claim is that if I measure the energy along the path of the curve on the outer surface, the boundary he calls it, he says that energy along the boundary is said to be equal to the area of the energy consumed inside of, or the interior of this particular boundary. He said, look, you can measure either what's happening here or you can measure what's happening on the inside. He said both are the same. Boy, that's pretty hard to get that conclusion, but he gets it, and we'll look at it later on. Yes, sir. Yep. This is only 2 dimension because it's given to us in 2 dimension. It gave it to us in x and y, right? If there was a k over there, then we're in the 3 space, and it would be a cylinder. But this is just going back to, high school math. Yep. Now, why is that important? I tell you, man, it's like the simple things is the key. Where am I with this problem? Where is it located? It's located in the x and y plane, not in the 3 space. That makes a big difference. Now, why is it? Here's what's cool, because I'm gonna use this example because this is where I exist most of the time. See, in the Bible, if you use that as an argument, when you study that Bible, you got to be very careful that you don't pull a scripture out and try to apply it somewhere that it doesn't apply to. So I have to first look at where that scripture comes from. Who was its intended audience initially? Is that audience there? Do I have similar properties of the audience that I'm dealing with today? Because I got to be able to relate it. So if he's talking to some widows over here in Acts chapter 6, and I'm dealing with some married women over here in my church, I can't apply that scripture. Because that goes back to I, J, and K. See that? I do harm to, if I'm trying to apply, and look, that's why, to be honest with you, that's why we're messed up right now. Because folk in the past have tried to apply these scriptures to situations and circumstances that you could not apply. If I'm in the plane, let me deal with the plane. If I'm in the space, let me deal with the space. but I can't cross it up. If I'm on just the one line, just on the x-axis, then let me just talk about that. And so we have to let people know that here's what's the setting here with these people, and let's see if we can find some correlation to where we are today. Okay. So now I got one for you. So no more preaching. Uh, okay, I want you to do that one. That's a class assignment. notice, the counterclockwise nature of the movement of a particle. That's what it's supposed to do in nature itself. So if it's in that direction, counterclockwise, you know you're on the right track. It's going from 0 pi over 2 pi 3 pi over 2. Yes, sir. Yep. Okay. So you get this, and then when you draw it, the direction is in that way. Right? Yes, sir. Because you get like x squared over 4 plus y squared over 4 is equal to 1. Then you just multiply everything by the 4, and you get x squared plus y squared is equal to 4. Okay. We want to find the limit here. First, you see if the limit exists at the value, and for all three, they do. So here, the limit of t of I as t goes to pi, this becomes just pi times I plus, let me change that plus, it's going to be a negative. We evaluate here t at pi, so cosine of pi is just -1. It's negative times j, and then that's plus sine of pi is 0 times k. Well, that's not OK or the OK corral. This is just pi I minus j, because 0 times the k is just 0. I'll call that back in calculus 1. If you can plug in the limit at the value, plug it in. If it exists, you're good. Move on. If it does not exist, if it gives you something silly, funky, crazy, then you have to go back and do some work, L'Hopital's rule or something like that. Right? But if you can plug it in, if you get a value, if it exists, it's not 1 over 0 or 0 divided by 0, nothing indeterminate, then you're fine. All right? Once you work that one, find the limit for that. If you're following along online with my notes, um, over the weekend, it's the same problem. I just typed over their class assignment. So um, when I post the lectures this afternoon for tomorrow, I will have them in there just like this with this format where it will say class assignment, okay, for the certain problems that I want to give you like that. Does everybody get it? Okay. Anybody still working? You got it? Let's see if you got what I have. And I got these answers late last night, so I don't know if I was in the third heaven or what. Maybe the second heaven, not the third. Did you get that? 6i plus 2 over 3j plus 1/2 k. Does everybody get that one? Good, good. Let me give you another one to do. Let's see if you can get this one. Now, that's a good one. That's a good one. With that, I'm going to step out because we have to holler. That third part, be very careful on that. You're going to get something if you recall calculus 1, an indeterminate form. this guy, we get 0 over 0, so it's indeterminate. So the first one is the limit of t squared as t goes to 0 times I plus the limit as t goes to 0, 3t times j plus the limit as t goes to 0, 1 minus cosine t over t times k. So for that first part, we get 0 I plus directly, we get 0 j. Here, since this is 0 divided by 0, we apply L'Hopital's because it's indeterminate. So this gives us plus the limit as t goes to 0. Here, the derivative of the numerator, the derivative of 1 is 0. The derivative of cosine is negative sign. Negative times a negative is positive sign t. And the derivative of t is just 1. So this is just times k. Then you evaluate t here, sine t at 0. You get 0. Determine the intervals on which the vector value function is continuous. What is this? What is this? What would the interval be here? The interval for continuity is tantamount to the interval that we will call the domain. They're saying the same thing here. Exactly. So t cannot equal to 0, t cannot equal to negative 1/2, correct? So you can write that if you want as from negative infinity to negative 1/2 union with from negative 1/2 to 0 union from 0 to positive. What's the domain for that? Okay, we know the restrictions. T has to be greater than or equal to 0, and t minus 1 has to be greater than or equal to 0. That is t greater than or equal to 0, and t is greater than or equal to 1. The and is the intersection. This and is a